Hi everyone, this is going to be a tutorial for how to use HXExpress version 3. We're going to specifically focus on bimodal spectra that you might come across and how to use the binomial function as a way to analyze those. So first thing we're going to do is make sure HXExpress works. When you download it from the website, you'll have access to these files. This HXExpress file is the one that's macro enabled. It has all the functionality you'll need. So first thing we're going to do is open that. And today I'm going to be working with Microsoft Office 365. It also works on Office 2016. I don't know if it'll work on versions previous to that, and I've never tested it on the Macintosh version of Office, so I can't guarantee any of that functionality. So when you first open it, you might see a splash screen. Just say OK. You might have to say enable macros. Once you are in that HXExpress worksheet, you'll see that this is the main sheet. This just has examples of what the data format will need to be that you import to process. You don't actually have to edit anything within this workbook though. So there's a sample data, there's statistics, and there's solver. None of this you ever have to mess with. So just leave that as is. But as soon as you open this workbook, you'll see that an add-in pops up here, and this is what gives you access to all the functionalities of HXExpress. If you don't see it, there's a few things you may have to do. So first off, if you go to File, Options, we have to make sure we have enabled some add-ins. So under the add-ins option here, if you go at the very bottom, Manage Excel Add-ins, Go, you have to make sure that you have the analysis tool pack, the tool pack VBA, and solver all checked before any of this will work. The other thing you might have to do is also in options, in the Trust Center, if you go to Trust Center settings, under macro settings, you'll have to select enable macros, which they say is not recommended. So if you plan on opening shady Excel files, then after you do this, you might want to turn it back. But to get everything to work in HXExpress, you'll have to enable this as well as select the trust access to the VBA project model. Lastly, you may also have to go to the developer tab and enter Visual Basic. If you don't see a developer ribbon tab here, then again, you can go to File, Options, Customize Ribbon, and make sure that you have this developer checked so you can actually see it. So if that's checked, you should have this option, which means you should be able to select Visual Basic. It pops up another window. This is how you can access all the code behind HXExpress if you ever want to look at that. But here, if you go to Tools and References, you will have to make sure that you have these two, this ATPVBAN, XLS, and Solver both checked. If they're not, some of the functionality won't work. So, okay, and that's really all we need to do in Visual Basic. So we're going to close that. So at this point, we've set up HXExpress. It should be ready to start processing data. So what we're going to do is open one of the first example files that is available on hxms.com. We're going to do the angiotensin bimodals example. So when we open that, this is just data that's been imported and it's already been curated, so it's ready to process. Real quick, I'm going to go over just the format. So it's going to be in these pairs of columns where the first column is going to be your M over Z. The second column is going to be your intensity. And the very top row is just going to be labels for your time points. Whenever you prepare data to process in HXExpress, you have to make sure that you don't have duplicate entries of the M over Z value. Sometimes when you export spectra from certain softwares, you won't have enough decimal places, and a lot of these entries will be duplicates. So if that's the case, go back, change how you export the data to fix that. You also don't want to have any blank rows. Lastly, sometimes I've noticed from thermodata, it puts in some weird text at the very end when you, depending on how you export the spectra. You don't want to have any of that. So if it adds any text to the end, you'll also want to trim that off. Otherwise, it's going to lead to errors. Lastly, the labels at the top for your time points. it's very syntax specific. So if you're not sure how to label these, there is a function here in HXExpress. So if we go to add-ins, Express, there's this add exchange time labels option. And here you could basically scroll through and select what label you want each of these pairs of columns to have. So the first one here is going to be an undeuteurated. This next one is a totally deuterated or a fully deuterated. And then here we had 1 minute. So if you hit enter, it'll update and keep moving on. You can always go back and forth. And then when you're done, you can say finished, and now you'll have everything labeled. So now you have all the XY data from all your spectra you want to process and the labels ready to go. So at this point, we can do the first step where we go to HXExpress, analyze spectra. Here it pops up this HXExpress parameters window. And here you can specify how you want it to summarize the data once it fits it all. Would you like absolute mass, relative mass, percent deuteration? I always just use relative. The time units, you can use whatever's comfortable for you. It has a smoothing option. I would recommend you smooth the data beforehand. Most mass spec software has probably more elegant smoothing than this software does. It can also do baseline subtraction, but again, if you can do this before you import the data, you're probably better off. And then in the analysis tab, here you have to specify the charge state of your peptide. In this case, I know this is going to be a 2+ ion. The distribution width is how wide you want it to look for when it looks through the isotopic envelope, or how low in percentage intensity it's going to look at. And you do want to use the isotopic peak detection for this step. If you want more information about these parameters, you can look at the very first HXExpress paper. I think it was from 2006 that describes all these parameters. So then if you say OK, it'll do the first process where it'll take all the data from that workbook and it'll process it. It'll do all the peak picking and do a very simple centroid measurement. And it pops up this new workbook that it made. It just called it Workbook 1 or Book 1. And this one has a bunch of worksheets. Each worksheet is one of the different time points that was in the pair of columns in our data that we imported. So this is the undeuteurated spectrum. You could see it picked all the peaks. You can see that in red. It did a centroid, which you see in green. And this orange is the width of the distribution at 10% max intensity. And if you scroll through, you can see it did this for all of them. This is our fully deuterated spectra, and these are various time points. The summary has all the information for all these time points and what the centroid was in absolute mass, what the relative deuteration is, and also that width at 10% max height. And down below are the plots. This is the centroid as a function of what time point it was, and this is the width. So after this step, what we now want to do is look at our data and see, okay, does anything look weird? And of course, we're going to be talking about bimodals today. So here's an example of a clear bimodal. This is actually synthetic in that I had a peptide that I either undeuteurated state or in a fully deuterated state. I mixed them 50-50 and I ran it. So that's why you see this nice, well-resolved two populations. So to handle something like this, what we're going to use is a binomial fitting approach. You can read all about that in the HXExpress version 2 paper from 2013. So for that, we're going to go to HXExpress, and we're going to use the binomial fitting option. And when you do this, it doesn't matter where you are, which worksheet you're in. As long as you're in the right workbook when you open this, it'll apply it to that workbook. So to do this, you have to specify a few parameters. It wants to know the number of amides. If you have 0 in there, it'll automatically guess from the sequence of the peptide. If you say optimize fits, it'll actually vary the number of amides to get you the best fit. And I highly recommend everyone start using that. You don't have to, but it tends to give you better results. The fitting asymmetry we're not going to use today. If you want to read about that, it's in the HXExpress version 2 paper. Then down here, it wants to know whether you want to read in the undeuteurated mass envelope from the undeuteurated mass spectra, or whether you want it to calculate it from the sequence. I always calculate it from the sequence because you don't know whether your undeuteurated spectra is really clean or not. So in this case, I know that this is our peptide sequence for angiotensin. I'm going to insert it there. I'm going to say calculate it from the sequence. If you want to add glycosylation to process a glycopeptide, that's all down here. If you have other modifications, say it was oxidized, you can put in an O there, say add custom modification, and it'll account for that when it calculates the mass. We're not going to do that right now because this is an unmodified peptide. So we're just going to leave that as is and say, okay. Now the computer is going to probably process for about 15 to 30 seconds. This is dependent on your desktop speed. But what it's going to do now is it's going to apply a single binomial fit to each of the time points and then summarize all that. So we're going to give it about 10 more seconds here and look at the data. It's faster when you do it on a high-powered desktop. I'm doing this on my laptop right now. Okay, I think it's almost done. Depending on what version of Excel you're using, sometimes it will actually update the screen so you can see the fits as they're happening. In this version of Windows, it just kind of blocks you out until everything's finished. Okay, that was the last step. Okay, so it pops you back to the summary window. And now you can see it's been updated. So instead of just showing you the centroid up to the width, it added 2 more columns. This is the labeling probability and the deuteration associated with the binomial fit. And this is the number of amides associated with the binomial fit. And down in the plots, now it also doesn't just show you the centroid that you had originally, but now it also shows you the binomial fit. So this is your deuteration level extracted from the binomial fit. And the width also shows you the number of amides used for every one of those time points. So if we look through all the actual worksheets now, you see that each of them will now have this blue line, which indicates the binomial fit. And it's a really good sign when your undeuteurated matches really well to the theoretical. It means you have a clean spectra and you have your peptide assigned correctly. You'll also notice that now the fit has this binomial 1, and then in brackets, there's a number. This is how many amides it used for the fit. So for example, here, it's actually not the brackets, ignore that. It's actually the number before the brackets. So this is the fully deuterated spectra. This blue fit is still fitting pretty well. And in this case, it's using 7.2 as the number of amides to achieve the correct width to fit well to the isotopic distribution. So the fully deuterated reference is actually a really good tool to have, or a good sample to have, because you can use that as a gauge for what kind of number do I actually expect for the number of amides for a pure population, because this is fully deuterated, it shouldn't contain subpopulations. So when we actually look at the deuterated data, so this was a single population, it's a nice fit, 5.5 amides. This is another great fit, 5.9 amides, another good fit, 6.6 amides. All of those are fitting so well that we have good confidence that those are just a single population that's unimodal. And then here, this was an original example where we had a synthetic mixture that was a 50-50 mixture of undeuteurated and fully deuterated. It fit well to one of them, but it ignored the other. And it's also flagging it because it's indicating that something about this looks weird and might be bimodal. In fact, the best fit here had 13.4 amides used for the fit. So that also is a good warning that there's something more happening within this spectra. And before we apply a double binomial fit, let's look at a couple of other examples. So here, for example, this is a mixture of undeuteurated and a peptide that was fully deuterated, but only in 50% deuterium. So here you still have two populations, but they're not nearly as well resolved. But you could still see that that single binomial just isn't able to fit well to the data. And in this case, you have 8.6 is the number of amides. And lastly, if we go a little bit further, we have this 9-minute mark, which was a mixture of a 25% or something labeled in 25% deuterium and something labeled in 50% deuterium mixed together. So this actually should be broader, and you can see from the fit, it kind of looks okay, but you're using 12.2 as the number of amides, which is way higher than that 7 that we had for the fully deuterated, which is why it's also flagging this one as potentially bimodal. So the number of amides here turns out to be a pretty good metric for detecting where you have way more broadening in an envelope than you expect. So let's go back to that really well-resolved bimodal. So now ultimately what we want to do is fit this to 2 so we can extract as much information about the spectra as possible. So the next thing we're going to do is go to HXExpress, and now we're going to use the bimodal deconvolution option. And that pops up another window. And we're only going to be using these top features for now. So you have this double binomial option here at the top left. If we click that while we're in this specific worksheet, it will apply 2 binomial fits. It'll minimize them, and then it'll pop up the best result it was able to achieve. And this might also take a couple of seconds for it to do. Again, if you do this on a high-powered desktop, it should only take at most a few seconds. Okay, there. So this is the best result it was able to come up with. So here in green is the fit for binomial 1. And then this is the blue fit, which was the second population. The dark blue here would be the sum, which you can't really see well, but what you can tell is it looks great. The fit was able to fit everything and explain the data really well. The second fit here used a number of amides at 7.1, which we know is about what we expect if you have a uniform population. So this is one thing here and another thing here. There's also this p-value that you see popping up in the total binomial fit. This is from an f-test that's used to determine the significance of whether you can justify using 2 binomials versus 1. And in this case, the p-value is way less than 0.05. So you have high confidence that yes, you can easily statistically justify fitting to 2 populations instead of just 1. So the lower the p-value, the better. Anything above about 0.01 or 0.02, I would think is definitely needs to be looked at more closely. So if we try the same example for, let's say, a bimodal that's not quite as well resolved, maybe let's go for this one. All right, we're going to do the same thing. Bimodal deconvolution, and we're going to apply a double. And in this case, this was a mixture of something deuterated in 25% D2O and something deuterated in 75% D2O. So again, 2 populations, but they're just not as well resolved. So let's see what the double binomial looks like on this. Okay, so again, by eye, it looks great. It was able to fit things really well. You get a total fit that matches up with the data really well. If you look at the p-value from the f-test, again, way less than 0.05. So you have high confidence that you can justify fitting this to 2 binomials. And through that, you can say, okay, there's at least 2 populations in this spectra. So the next thing that you can try to do is to actually extract information for what the relative deuteration and relative intensities of each of these 2 populations are. So that's already kind of given here. So in cells I, 16, and 17, this is the relative intensity of the population 1, which is the one in green. So that would be 41.1% of the total intensity. And this would be the second population in blue. That's 58.8% of the total intensity. And then here, average D1 and average D2, these are the deuteration levels of the green and the blue, respectively. So one thing you have to really be mindful of is no matter how you fit the data, you're going to get numbers for these. However, you might not necessarily be able to trust those numbers. And we'll see an example of that in a second. So for example, here, this is also a bimodal. This is a mixture of something that was 50% D2O or 100% D2O. If we apply the double binomial, we will see that, yes, it's going to be able to fit two populations. They're probably going to fit really well. We may even have a p-value that's highly significant, but we might not necessarily be able to trust the numbers that it gives us in terms of relative intensity in the deuteration state. So here are these are the relative intensities. The green population is 45%, blue population is about 54.6%. But you can see that they're not that well resolved. There might be a whole bunch of ways to fit two populations in there that are almost just as good of a fit. And anytime you're in this scenario, you lose confidence in terms of how accurately you've really pinned down these numbers. So to address this, we built in another function. So if you go back to binomial or bimodal distribute or deconvolution, now instead of just hitting double binomial, if you check this perform bimodal statistical analyses box and then do a double binomial, it'll do the same thing again. However, it does an extra routine where it looks at all the regression metrics through all of the fitting that it did. And it uses that information to extract a standard error for each of the parameters that it's able to extract for these fits. And by looking at those standard errors, we can actually get a pretty good idea of how well we can trust the numbers. So here's what it looks like. Again, you see the two fits. It still pops up the same values here. You see there's now 3 additional of these graphs that popped up. I'll explain those in a second. And now there's also all this information down here. These are basically all the statistical results from how it was able to do this nonlinear regression fitting. So from this data at the bottom, for each of the parameters that fit, it was able to get a best value and a standard error of the fit. So in this case, if we're looking at, say, the relative intensity of the green population, that would actually correspond to this C1. This was the value and total intensity that it was found to get the best fit. This is the standard error associated with it. And if you look at this CV percent, that's actually the percent error associated with it. And that's actually not that low, meaning that in this case, you could say, yes, the green population is about 45% of the total population, but with an error of 24%. And the same goes for the blue. The blue population is 54.6% of the total intensity, which is statistics are down here, but with an error of about 20%, which is kind of high. And that's actually what is embodied here in this first additional graph that popped up. So this bar graph basically represents how confidently it was able to fit all of these parameters. The higher the bar, the better it was able to fit, and the higher confidence you have. These 3 horizontal lines represent confidence intervals. The green would be 99%, the orange is 95%, the red is 80%. So the height of the bar here is basically how confident you are in these values or these values. The other 2 graphs that popped up are used as secondary ways to assess whether you can trust those parameters from the fit or not. The delta chi metric looks at how well or how much did the signal or the fit improve using 2 versus 1 binomial. So it's very similar to this p-value, but it's useful in that you also have these thresholds of significance that you can use to assess how good the fitting is. And lastly, the separation metric, it looks at how far apart are these two populations in terms of their deuteration levels. The closer they are, the lower this bar will be. And in theory, if they're really close or on top of each other, you shouldn't really be able to get any kind of information out of it just because they're not well resolved. So really, when you're looking at the data and you want to assess, all right, can I actually extract these numbers with any confidence? I would look at this graph first. Every once in a while, because of the fitting, if it's some kind of weird noisy data, it might get stuck in a local minimum. And I've seen a few examples where this is actually still higher than the green, but these are really low. So I would mostly go off this, but if these are low, they're kind of used as sanity checks to make sure that you're not over-interpreting something that was just in some kind of a weird minima during the fitting process. So let's see what this actually looks like for a well-resolved bimodal. So here's that first example. We're going to go back and we're going to repeat that double fit, having this perform bimodal statistic analysis on. Yeah, it takes a little extra time when you specify doing the statistical analyses, but again, this should be much faster on a high-powered desktop. Okay, so this is what it looks like when you have a really clearly well-resolved bimodal. So if you look at all of these, the bar graph height is through the roof. You're way above that 99% confidence interval. And that's what you expect. I mean, by eye, you can readily tell these are super well resolved. You can probably even fit these by hand if you needed to. And then if we look at an intermediate case, let's say this one, we're going to do the exact same thing with statistical analysis. We're going to do the double binomial. Okay, so it popped up the result. And again, these two populations are well enough resolved that you still have really good confidence in these values for the relative intensities as well as their deuteration states. So one last example I'm going to talk about is going to be here towards the end. And this is going to pertain to what if you have more than two species in there? So we're going to take this data, which kind of looks like a mess. It's definitely got more than one thing in there. You can already tell from the number of amides. We're going to try the first step. We're going to do a double fit and see what we get. Okay, so it did the double fit. The metrics don't look that great, but you can also tell by eye that the fit actually does not look that great. The distribution of the data here looks broader than it's able to fit. And it's also doing this weird thing where it's shifting the baseline up to try to fit this better. So clearly there's something else happening here. So if you come across something like this, what you could try, and there's functionality built into HXExpress, is a triple binomial. It's kind of risky in that you're entering the realm of potentially overfitting because you'll have so many parameters that you may not even have enough data points to justify using that many parameters. But in some cases, this might lead to potentially give you some more insight into what might be happening in your data. So we're going to try a triple and see what it looks like. Okay, so it did a triple. Here's that third population now. And yeah, it looks great. I'd be surprised if it didn't look great. With a triple fit, you have so many parameters you can adjust. It'd be kind of hard to imagine a scenario where you don't fit great. But you see from this p-value from the f-test, the p-value is 1. And this has to do with the fact that you don't have enough number of points in the data to give you the degrees of freedom you need and all the parameters associated with the fit. So in this case, you can't statistically justify that you have 3, although there's by eye good evidence you do. Also from this, you may have this first population in green pretty well constrained, but these two are probably too close together and you don't really have enough to really say this relative intensity compared to this relative intensity with any kind of confidence. I mean, the numbers are all here, but I would be very cautious in how you interpret things like this. So that's the last thing I want to leave this data with. It is possible to do triple binomial fits. I would approach it with a very high degree of caution. Okay. And the last example that I wanted to go over is looking at pulse labeling data. So I'm going to close that entirely and open one of the other example data sets that's available, which is called the pulse labeling data example. So again, this is all formatted already. It's got the time labels. So this one's going to go from 1 to 60 minutes. And in this case, we're actually looking at an unfolded protein folding over the course of 60 minutes and getting a consistent pulse of deuterium. So again, the first step you need to do is take the data, do an analysis. This is also 2+ ion. Say okay. This will do that initial peak picking and centroiding. Okay, that's done. So here's the summary page. And you can see that it was able to look at all the data, pick the peaks, and you can see here's what's happening. You have this population, which corresponds to the unfolded state, over time shifting to this less deuterated population corresponding to the folding state. And as you go longer and longer, you see this population decrease and that population increase until the very last time point where it's basically all gone. And at this point, it's 100% folded. So what we want to do in this case is use that double binomial approach to actually extract out the kinetics of how fast this folding process is happening. So to do this, again, the first step we need to do is apply a simple binomial fit. So here again, I'm going to optimize fits. If you have 0, it'll automatically estimate it from the peptide sequence. I'm going to say calculate, and I'm going to paste in the peptide sequence from here. No modifications or anything like that. Say okay. And again, this will probably take half a minute or so for it to go through the entire data set and do a single binomial. Okay, summarizing the data. All right, so it updated the summary. So now we have all of the deuteration levels here from the binomial fit, the number of amides here. And if we look through the data, again, the undeuterated fit really well to that binomial, which is good reassurance. As we look through the time points, we see that, okay, fit well to the unfolded state here. And then as you go later in time, of course, that single population is not gonna, or the single binomial is not gonna fit well once you have more than one thing in there. So now what we wanna do is we actually wanna fit the double binomial to both of these. So first thing I'm gonna do is just select one where I see both populations pretty well resolved. let's go with this one. And I'm going to use the bimodal deconvolution to do a double, just a standard double up here. Okay, so there's the result. So it's saying that the first population has an average deuterium of 2.6 using the labeling probability of 0.375 and 6.9 amides. The second population has an average deuterium of 7.8 using a probability of 0.737 and 10.58 for the number of amides. So for pulse labeling data, one of the new features we offer is this restrained double, triple, or even quadruple fitting. So what you could do here is if you already know the deuteration levels or the probability of labeling and the number of amides associated with each of these, you can input those, restrain them, and get through the fitting faster and potentially get more accurate intensities, especially for where one of those populations is not well resolved. So if we were to do this, let's say we know that population 1, this one, has a labeling probability of 375 and a number of amides of 6.9. And population 2 is 0.373 or 737 with 10.58 as the number of amides. I can now say, okay, do a restrained double fit where it'll keep these constant, but only vary the relative intensity of each population. All right, restrained double. And I'm basically just testing this on that same data set and see how it behaves. Okay, we pretty much get the same answer, which is not surprising. But the reason this is helpful is now we can go to all of the other spectra that have two populations in there. Go back here, everything is saved. So you can basically just click restrain double again and keep everything restrained to those same parameters that you had before. And what's actually really helpful is if you have a full data set where you know that these are the two populations that you want to fit to, there's this option that you can check apply multimodal fit to all spectra. If you have this checked and you say restrain double, it'll basically use this and fit all of your time points except for the undeuteurated or a fully deuterated. That way you don't have to sit here and keep clicking and doing this one after the other. So what I'm going to do is I'm going to actually close this and open a processed version of this so we don't have to sit through here. So this is what the end result would be. So here is the fitting result using that restrained bimodal or double binomial all the way through. Once you've done that, the last step is go back to that bimodal deconvolution. And now you can use the summarized double option here, which will basically extract all the relevant information and add it to that summary worksheet at the very front of this workbook. If you use triples, you can also use a summarized triple. If you end up using 4 populations, which will be very rare, I've only ever seen one instance where I could convince myself that there was more than 3 things happening, then you can use the summarized quadruple here. Right now, we're just doing the double. I'm going to say summarized double. It updates the summary sheet so that now it's showing you the deuteration level of both populations the number of amides associated with both populations. And critically here in that third graph now, it's showing you the deuterium level in the circles and the solid lines. But now this is a double y-axis plot. So the dashed lines now correspond to the relative intensity of population 1 and population 2. So in this case, this was the more protected, less deuterated population, the folded state. This was the unfolded state. So through the course of folding, you go from almost all unfolded protein, and the population of this drops as you fold, and the population of this grows. So this plot has both the deuterium information as well as the relative population size information. It's basically replaced the bubble plot that we used to have in earlier versions. And the summary sheet itself will have all of the relevant information for the relative intensities of populations 1 and 2 here for all of your time points, as well as the labeling probability and the average deuterium level for population 1 and population 2 here. The last thing I'm going to point out, which is a function that you might not need because most people will just use HXExpress to do these fits and then move the results to whatever program they want to do any other fits with. But if you want to just do a quick exponential fit to how these populations change over time, there is a function for that down here. So if you want to fit a single exponential to, say, this blue dashed line, you would say, select the population for exponential fitting. I'm going to do binomial 1, so the first population. I'm going to say, try to fit that to a single exponential, and let's see what we get. I'm going to give it a second. Yeah, there, it updated. So when you do that, it pops up another graph here. This in red is basically the same data as the dashed blue here. So this is the population of the folded state growing over time. The black dotted line represents the exponential fit for a single exponential. And as you can see, it doesn't fit it as well as it could. There might be other processes happening. Sometimes it actually takes a double exponential fit to achieve a good fit, which we also have. So you can do a double exponential. Again, we're fitting to that first population. When you do this, it'll update that fourth plot. It just takes a second. There it is. So now you can see that using a double exponential fit, you actually have a pretty nice fit to what the results show. And that's basically all I have today. If anybody tries this out and runs into problems, then please look at the release notes, contact me, and let me know what the error is. It's very helpful if you also send a screenshot as well as the file that you're trying to process. So good luck.